All right, let's look at an example where we're asked to find all possible rational zeros of our function. It is a fourth degree polynomial. It's already in descending order. And the first thing that we are going to do is list all possible rational zeros. When we're doing this, remember, this is where we do plus or minus p over q, where p is our factors of our constant term, which is 10, and q is our factors of our leading coefficient, which is 1. So factors of 10, using the rainbow method, we have 1 and 10. Next number up from 1 is 2. 10 divided by 2 gets me 5. Next number up from 2 is 3. 10 is not divisible by 3. We get a decimal. Next number is 4. 10 divided by 4 again gets us a decimal. Next number is 5. So we've completed the rainbow. We have all the factors of 10. And factors of 1 are just 1. So when we do our plus or minus p over q, and remember, I'm going to list these with the plus or minus out front. We're going to take each of these values of p, the factors of 10, and divide them by 1. So 1 divided by 1 is 1. 2 divided by 1 is 2. 5 divided by 1 is 5. And 10 divided by 1 is 10. If I were to list these separately, I would have -1, +1, -2, +2, -5, +5, -10, +10. So you could do this either way. I just prefer the shorthand of the plus or minus out front because it's less work for me to write. We need to use synthetic division to find a zero of h of x. Remember, with the rational roots theorem or rational zeros theorem, we've taken an infinite number of rational numbers, which are integers, whole numbers, and all of our fractions, the rationals that we think of, right? And we've narrowed it down to these 8 choices. But even then, we do not have to try to guess and check which number we're going to put in the loser corner first. Instead, if we look at the graph, and I used desmos.com/graphing, you can see that we have a 0 at -1, 0, a 0 at 2, 0, and a 0 at, should be 5, 0 if I could touch the number, but it's not working for me right now. There we go. All right, so there we have our zeros, and we're going to pick one to plug into the loser corner for synthetic division. Doesn't matter which one we use. I'm going to work from left to right, so I'm going to use -1. And remember, we are only going to take the coefficients from our original polynomial. So on the x to the 4th, we have 1, and then -5, -3, 13, and 10. Give some space for yourself, give yourself the horizontal line, and let's begin. The first one always comes down. -1 times 1 gets us -1. Add vertically. -5 plus -1 gets us -6. -1 times -6 gets us a +6. Add vertically, we get 3. -1 times 3 gets us -3. Add vertically, we get 10. -1 times 10 gets us -10. Add vertically, we get 0. And remember, 0 in the remainder column tells us that x equal -1 is a 0. And we also know that x plus 1 is a factor. Okay? We need to find all other zeros after this, but doing that, we are going to use our remainder polynomial. Remember that we started out with x to the 4th, x cubed, x squared, x, and then the constant term, the number. Going down 1, because we were dividing the factor x plus 1 out, we're going to have x to the 3rd, x squared, x, and then a number. So our remainder polynomial is going to be 1x cubed minus 6x squared plus 3x plus 10. Now, technically, if you could factor by grouping on this, go ahead and have at it. But this one doesn't work as nicely as the others that we've tried factor on grouping, so I'm just going to keep moving forward. I'm going to do another synthetic division using one of the other zeros that we found. So let's say this time I use x equal to 2. Using the remainder polynomial coefficients, up top we'll have 1, -6, 3, and 10. First one always comes down. 2 times 1 gets us 2. Add vertically, we get -4. 2 times -4 gets us -8. Add vertically, we get -5. 2 times -5 gets us -10, which gets us 0. 0 in the last column means that x equal to 2 is a 0. And that also means that x minus 2 is a factor. If we're looking for the remainder polynomial, remember we had worked with an x to the 3rd in the blue. So dropping down, we're going to have an x squared, x, and then a number, which means that our new remainder polynomial is going to be 1x squared minus 4x minus 5. Okay, you could factor this. I know most of you hate factoring. So let's say that you continued with your synthetic division, just for the heck of it. Because we did -1, we did 2, we can still do 5. We haven't done that one yet. And then my coefficients would be 1, -4, -5. Remember, the first one always drops down. 5 times 1 gets me 5. Add vertically, we get 1. 5 times 1 gets me 5, which gets me a 0. We just found that x equal to 5 is a 0. And we also found that x minus 5 is a factor. But this isn't done yet. A lot of students stop here, which is why I went this method. Because we had an x squared. This is an x, and then we have our number and remainder. So our new remainder polynomial is going to be 1x plus 1. Set it equal to 0 because we're finding a 0. We're finding an x-intercept, a root, a solution. All the same thing. Subtract the 1 and we get x is equal to -1. Which means that x equal to -1 is a 0, and x plus 1, or 1x plus 1, is a factor. We found all the factors. We found the zeros. We found 4 zeros. Okay, so let me scroll up a little bit. We found x equal to -1 is a 0, and x plus 1 was a factor. That was our very first synthetic division. I'm going to make that one. I'm going to color code here. X equal to -1. I'm going to write it in black just so color coding here is going to come into play so you can see where everything's coming from. We had x equal to 2 as a 0, which gave us x minus 2 as a factor, x equal to 5, and x minus 5 as a factor, and then x equal to -1 again with x plus 1 as a factor. So in the next step, when we're asked to find the factored form of the polynomial, you should not be trying to reinvent the wheel. You already found all the factors. The very, very first one that we found was x plus 1. This is why I color coded, went back and changed it. Because we had x equal -1 as a 0, x plus 1 is a factor. And then we found x equal to 2, which gave us x minus 2 as a factor. And then we had x equal to 5, which gave us x minus 5 as a factor. And then finally, we found x plus 1 again. You could technically leave your function like this, but we can make this a little bit nicer. And I can't call it p of x because the original one was h of x. I'm not going to change the guy's name. Notice that we have x plus 1 showing up twice. That means that we have x plus 1 quantity squared times x minus 2 times x minus 5. Remember that you can write your final polynomial with the factors in any order that you want. They are commutative, they flip-flop. So if you had the x minus 2 first and the x plus 1 squared last, that's fine.